Hello everyone. I am Hassan Al Banna Himel. I am presenting my screen with you, and further on, I will let you give me my proper introduction. Can someone confirm me that if they can see my screen? Yeah, thank you. Uh, Let us start our today's session. Hello everyone. I am Hassan Al Banna Himel. It is day 3 of linear algebra for artificial intelligence and machine learning. I am currently studying at first year and pursuing my BSc in computer science and engineering from Brack University. Today's session is supported by Global AI Community, Dev Changemakers, NSDC Brack U chapter, and TensorFlow User Group Bangladesh. Uh, in today's session, we will look through these contents. We will go through matrix operations, some of the things we discussed in our day 2. It is day 3, and we will start where we last ended our session. And secondly, we will discuss about matrix calculus, some of the matrix calculus. If you have any question, you can raise your hand and I will then hear from you. Am I clear? Yeah. So let us start. In today's session, in matrix operations, we will look through in these points. We will discuss about scalar multiplication, matrix multiplication, transpose of a matrix, determinant, inverse, and finally trace. Now, if we look further in our slides, what is a scalar multiplication? If I have a matrix, uh, here we can see it is a 3 by 3 matrix. If we have given a matrix and a scalar, if we think this matrix is matrix A and it is a constant of scalar value C, the scalar multiplication C multiplied by A is calculated by multiplying each element of A by C. We can see that here the constant 2 is multiplied by each element of in this matrix. We can see here that this 2 is multiplied by 1, then 2, then 3, then second row 4, 5 and 6, then third row 7, 8 and 9. In our further calculation, we saw that 2 multiplied by 1, 2 multiplied by 2, 2 multiplied by 3, and then 2 multiplied by 4, 2 multiplied by 5, 6, 7, 8, 9. And finally, we can get our matrix, final matrix. Let's assume it as matrix Y. Matrix Y finally came 2, 4, 6, 8, 10, 12, 14, 16, and 18. Then if we go in our next slide, in this slide we're discussing about matrix multiplication. In our previous slide we discussed about scalar multiplication, and now we are discussing about matrix multiplication. So we can, in the last slide we see how we can multiply a scalar to a matrix. Now we will see how we can multiply a matrix with another matrix. If we look in the definition, it says if you have matrices A and B, let's assume it as matrix A and let's assume this as matrix B, the product AB let's assume the final product as y, and the output will be AB. The product AB is calculated if the number of columns in A matches the number of rows in B. We need to see it carefully. If our matrix A's number of rows matches with the columns number of matrix B, then we can multiply these matrices. If you want to multiply like uh, 1 2 3 uh, 2 2 1 with another matrix 1 2 uh, just a second, yeah, 1 2 3 4. Here we are seeing 2 by 3 matrix, 2 by 3 matrix, and here we have a 2 by 2 matrix. If the value of values in the row, I mean values in the column, does not match the value of rows, you can't multiply this. Again, to find the final product, you need to multiply with the number of rows with the number of columns. Here we will multiply 1 with 10, then we will add 2 multiplied by 20, 3 multiplied by 30. That will be our element of first row and first column. Then we will continue this with our second row, our second column. Here we are multiplying 1 with 11, then 2 with 21, and 3 with 31. Here we get the element of first row and second column. Then on the first column and second row, in that element we will multiply our matrix A's second row at first, then with the B's first column. We will multiply now 4 multiplied by 10 plus 5 multiplied by 20, and finally 6 multiplied by 30. And in our final second row and second column, in this element we will multiply 4 with 11, 5 with 21, 6 with 31. And after done, when we're done with the calculation, we get this 2 by 2 matrix, and this is our final product, our y, and as we knew before, y is equal AB. Now let's move to the our next slide. Sorry. Yeah, so here we have transpose of a matrix. The transpose of a matrix A. Let's assume this matrix as A or B or C. You can annotate with anything and denoted A transpose T. If we can write this like A subscript T is obtained by switching the rows and columns of A. Look, now if we look at in this A matrix and assume this is the output, our A transpose matrix, here our rows becomes the columns and the columns became the row. Here the 147, our first column, turns into the first row. We can see here our first column 147 here became our first row 147. Our second column 258 in the final output became the second row, and our third column 369 finally becomes the third row. As this is like you can turn any matrices in this form. This is not mandatory that need to be a square matrix, I mean 2 by 2 matrix, 3 by 3 matrix, 4 by 4 matrix. It is not mandatory. You can do it with any matrices. It can be a 1 by 2 matrix, 3 by 4 matrix, 7 by 8 matrix. and anything, any matrix you want. Now let's move to our next slide. Let's now now we will look at the determinant. What is a determinant? If we look to the definition, the determinant of a square matrix A is a scalar value that can be calculated using a variety of methods. The determinant has various geometric interpretations and properties related to linear transformations. This determinant will help us in the further stages when we will learn about linear transformations. We will learn about vector and vector spaces and subspaces in our upcoming days. Now if we look at our determinant, let's see. Here we have a matrix with 9 elements, 3 in each row and 3 in each columns. If we want to find the determinant of the matrix, we need to multiply the first row's element. Like in this first row we have A, B and C. Now if you want to find the determinant, at first you need to multiply our first rows and first columns, I mean first element, and also called 1 element, with the with while we cover our first row and first column. In this time when we are multiplying with A, we will covering first row and first column. We covered our first row and first column. The leftover things will be multiplied. Like here we are multiplying E with I, and then we will subtract with F multiplied by H, and then furthermore we will multiply. There is a subtraction sign. We will then multiply B with, now we're closing this row and this column. Here you can use a trick that which row you are counting, you will cancel that row and you will cancel the row where the element is belonging. Here we will multiply B with DI and subtract GF, and finally if you multiply with B, you will find the output. And same goes for C. This column and these rows are cancelled, and this is how we can find a determinant. In here we can see that in terms of cofactors, how can we find the cofactors? The element which is multiplied, the first row and first column was cancelled, and the leftover elements are called cofactors. As we know that matrix multiplication, we are going to multiply in orthogonally. We will multiply E with I and F with H, and secondly while we are doing it with B, we will multiply D with I and G with F, and finally when we are multiplying C, we can multiply D with H and E with G. Now let's move on to our next slide. In this slide we can see that what is a inverse matrix. If we look in the definition, the inverse of a square matrix A, denoted as A superscript -1, exists if A is non-singular, as if it has a non-zero determinant. In the previous slide, we looked through that the how we can find determinant. If your determinant of a, if we have a determinant a is not equal 0, then you can find its inverse. If your determinant of a comes to 0, you can't find the inverse of that matrix. Then if we go to our next slide, here we have trace. Here we are looking of trace of a square matrix. If you want to find the trace of a square matrix, let's assume it is a matrix A. It will have 9 elements, or 4 elements, or you can say 1 element. It can be 1 by 1, 2 by 2, to infinity, n to n, and many more. It can be more. Here we are discussing about 3 by 3 matrix. It has 9 elements: A11, A12, A13, A21, A22, and A23, and finally in the last row we have A31, A32, A33. If we want to find the trace of this square matrix, we need to sum the diagonal elements, or the main trace, or the main diagonal. Here A11, A22, A33 is our main element. If we look in a matrix that has 4 elements, like 1, 2, 3, 4, the diagonal elements will be A11 element, or 1, and A22 element, or the element denoted as 4. And if we want to find the trace of A, we're doing this math for this matrix. We are going to have 1 plus 4, and the trace will be 5. That is for our matrix operations. If we have any questions for now, you can ask me, then we will discuss. Yeah, Manuel, do you have any questions? Yeah, Siam.
Would we get the idea of the purpose of the operations that we discussed before? Like, what is the purpose of inverse matrix and the trace? How can we benefit from it and things like this?
Thank you. With this matrix, and after learning this method, this is the basics of the matrix, we know that. And when we will go further, like when we will do linear transformations, linear regressions, and while doing with works with big data and like that, we need to know about these calculations.
All right, thanks.
Yeah. Now let's move on to the matrix calculus. Here today we will discuss about two things. We will discuss about Kronecker product, how we can do or how we can find the Kronecker product, and secondly we will see types of matrix derivatives. We can do this in three forms. We will discuss one of that today, and the other two methods we will discuss in our next session. What is a Kronecker product? The Kronecker product is a way to combine two matrices A and B to create a larger matrix by multiplying each element of A by the entire matrix B. Here we have a typo. Sorry for that. Now, if we look in a picture, what Kronecker product looks like. Here we have two matrices. Let's assume this as matrix A and this as matrix B. In matrix A, we have four elements 1, 2, 3, 4, and in the matrix B, we have four elements 0, 5, 6, 7. While we are doing the Kronecker product, the sign of the Kronecker product is the multiplication sign is in a circle. While you are doing with this sign, this means you are finding the Kronecker product of these two matrices. If we look at the Kronecker product, you need to multiply each of the first matrices element with the B matrices products. If we look at it, we have the first element, it is 1, and if we look at the B matrix, we will multiply it with the whole matrix. We will do it with other three elements too. Like here we are doing 1 multiplied by matrix B, then 2 multiplied by matrix B, then 3 multiplied by matrix B, and finally we're doing 4 multiplied by matrix B. We know how we can do the matrix multiplication. Now we will multiply in that way, and in the first slide we saw how we can do the scalar multiplication. In here we will do that scalar multiplication. We're doing it with this constant 1 1 with each of the elements of B matrix. We are multiplying 1 with 0, 1 with 5, 1 with 6, and 1 with 7. We can divert we can divide it with these lines. We can say what is the which elements of the which part of the product or which part of the matrices. We are doing the multiplication 0 over 0 multiplied by 1, 0, 1 multiplied by 5, 5, 1 multiplied by 6, 6, and furthermore we're doing this. Finally we can see that here, while we're doing multiplication, we multiplied a matrix which is a square matrix and which is the dimension of 2 by 2. These sorry for that. This matrix is dimension of 2 by 2, and when the final product we get, it becomes 4 by 4 matrix. Yeah, it has 4 columns and it got 4 rows. Now if we look in another bigger matrix, let's assume this as C and this as D. We will sorry for that. We will multiply each of the elements of C with the matrix D. We're doing it with every single elements. This quadrant or this part belongs to 1. If we look at it, 1 multiplied by 8, we got 8. 1 multiplied by minus 9, minus 9. We all can say that how it is done or what is done here. And in the next part here, we are multiplying with this whole matrix with minus 4, and then we're doing the whole with minus 7, and in the second row or while the second part we are doing it with minus 2, then 3, and finally 3. This is how you can get the Kronecker product of two matrices. And we came to our final part by now. Yes, I know it is a short session, but due to my finals I have to do this. This took short times, and in the future sessions I will try to include more topics in the sessions. Let's now continue our session. Here we are looking at types of matrix derivatives. In today's session we will talk about derivative with respect to scalars. Other than that, we have two more. We have derivatives with respect to vectors and derivatives with respect to matrix. We are today in today's session we will doing only the derivatives with respect to scalars. In the next session we will do the derivatives with respect to vectors, matrices, and in next session we will also discussing about linear transformation, vector, and vector spaces and subspaces. Now if we look in our next slide, we can see we're discussing here the scalar. You can derive it a scalar with another scalar, a vector, and with a matrix. We will today we will be doing this one, and in the next day we will be doing the vector one. We can do vector with scalar, and vector we cannot do vector with matrix, and finally we will do matrix with scalar, as we will be seeing today that we are going to do with the scalar one with matrix, and that will be our derivative part. Here we are going to derive it with respect to scalars. Here we have a function y with sine x square, another vector with x, cos x, and 2x square, and finally we got a matrix y in the elements. First element as x squared plus 1, second element cos x, third element sine x, and final element x minus 1. We're doing it here. If we do this, we all know that the the derivative of sine x squared is we can do this d dy dx will be our 2 sine x. Sorry. We know that it will be 2 cos x, and then when we do with the y1, that y vector, we will be doing the y vector sign, and with respect to x we will get a vector of, we will do the derivative of x, we will get 1, while we are doing the derivative of cos x we will get a negative sine x, and when we are doing it with 2x squared we will get 4x. And finally when we are doing it with a matrix we will get the dy dx. We're doing it with respect of x. We will do it the simple way, or we all know the rule how to derive it this, or how to do the derivation. We all know that. While we do that we will do the simplest way we all know, which is it the 2x, it will derive 2, and as it is a constant it will be 0, and the second element cos x will be negative sine x. The third element or the second row first column element will be cos x, and the final element or our 2 element will be 1. And we know that as this is a constant, it own it will be 0. That is from my side for today. If you guys anyone have any questions or any query, you can ask me with while raising up your hands. Yeah, Siam.
Wouldn't we discuss the applications of those topics in AI and machine learning?
We will discuss in further classes. We are currently clearing the basics, or some people don't know the basics about these things. We are now covering the basic things, and in the further classes we will connect this with machine learning and how you can utilize this in the machine learning or data science and in these things.
Alright, thanks.
Anyone else got any questions? Any date schedule? uh we will do maybe in next week, or next Sunday or Monday will be the next date for the next session. You will get it from my LinkedIn. I am dropping my LinkedIn here. Just hold, give me a second. You can follow me in LinkedIn, and you can also follow me in GitHub. This is from my side. You can share your experience with me. How was the session, or if we have any suggestions to give me, as I am a newcomer or I can improve this, you can say. Any suggestions will be appreciated if you give me any suggestions. Thank you, everyone. This is from my side. You can leave now. Thank you, everyone, once again. I am closing the session. Again, thank you.